Okay. You guys remember conservation energy? Remember that? You remember that? And before we did a little rotational, but if we were just doing like an object falling, it's K naught plus UG naught equals K plus U. Right? What if I subtracted K naught from both sides? What would I have on the right side? I'd have K minus K naught. What could I write there?
Delta K.
Delta K. What if I did the same thing with UG naught?
Delta UG.
Plus delta U. And what would be left on the left side? Zero. Another way of looking at conservation of energy. The change in the kinetic energy plus the change in the gravitational potential energy has to equal zero, meaning if one goes up, the other must go down. So, if I want to change the energy in the system, what do I have to do? Starts with a W. Work. I have to do work. So I can change the system's energy by doing work. And let's say that I'm going to do work, just hypothetically. I'm going to do work and I'm going to maintain a constant speed. So if we're talking like gravity, I'm going to lift a weight and I'm going to do so at a constant speed. Okay? In which case, I'm not going to have a change in kinetic energy. So what I will end up getting is the work I put into it will be equal to the change in gravitational potential energy. Make sense? Conceptually, what if I had a charge here and I had a charge here, little q, positive, and I had a charge here, same charge, little q, positive. Do you think, and this guy's fixed, right? This guy I'm holding on to, I'm not letting him go. And these two I just let go. What's going to happen to them? What are they going to do?
Repel.
They're going to repel, they're going to accelerate that way, right? We know that intuitively. Well, what's doing the work there?
Electric field.
The electric field, the electric force? Of course. So and thinking of it in terms of the field is actually pretty good. The electric force is going to do work on this guy, changing some type of energy into kinetic energy. What type of energy is it changing? Electrical potential energy, right? How do I know how much electrical potential energy that guy has there? It's just the amount of work I got to do to put it there. When I lift the bowling ball. When I lift the bowling ball at constant speed again, because I want to keep this simple and not have to track a change in kinetic energy as well. If I lift this guy at a constant speed, then I'm giving it more potential energy, right? Sorry, by doing work. I think I'm saying the same thing over and over again.
So if you were changing kinetic energy, would the equation be the same, but just with kinetic energy on there?
It would get a little more. I'm trying to get at the heart of a definition of something, and so with that definition, we'll be dealing with conservative forces. So yes, that's a good question that we will answer soon. Okay. If you didn't hear the question at home, that's okay, since half of this class is at home today. So yeah, so this guy has to have potential energy there, right? And that means that I had to do work to put it there, right? Because if I wanted to store that potential energy, I would have to work on it to put it there, just like I have to do work on the bowling ball to lift it, just like I have to do work on a bowstring to store potential energy in a bowstring, or to stretch a spring, anything like that. So this guy's obviously got more potential energy, this guy's got less potential energy, right? And so the definition, or how we can determine what the potential energy of that guy is just how much work is required to put it there. But because the electric force here is going to be repelling, we got to be a little more careful, because if we have a negative charge, it's kind of the opposite, which means we're going to be dealing with negative potential energies and positive potential energies, so just kind of be ready for that. But let's actually do this formally. Let's actually say, all right, this Q, I want to bring in the presence of this charge here and determine how much work is going to be required to do so, okay? And the work that I do is going to be exactly equal to the potential energy that I will store. This will have the same meaning. We're just going to change the G's to E's, okay? But the same, we get the same. It's a little more complicated because the field strength won't be constant here. As it moves away, the field strength will reduce, whereas on the surface of the Earth, the gravitational field strength is the same pretty much. So it's a little more complicated, but in essence, it's the same thing. As long as I try to keep it just moving from one bringing an object to that location, how much work I need to do is how much potential energy, electric potential energy I've stored. Does that make sense? Well, how did you store 100 joules of potential energy in the bowstring? I had to do 100 joules of work, right, to do it. Now, where are we bringing this charge from, though? Like, let's say I want to bring that charge. I should have said this first. I want to bring that charge to right here. Charge little q. I want to bring it to a position relative to this guy, and this guy's going to be the fixed one. I want to bring it to a position R. I want it to end up there. Well, where am I bringing it in from, do you think? If I'm doing, this is going to be a rigorous definition. It is literally the amount of work required to put this guy there. Put him there from where? Infinity. Infinity. Very good. Nice. Yeah, we're coming from infinity. How much work is required to bring an object from infinity to a location, a charged object, in the presence of an electric field? We say from infinity. But Mr. Graham, the infinity doesn't exist. You're learning in calculus. We do infinities all the time. Calculus is all about infinities, right? We can deal with infinities mathematically. It's fine. Are we actually taking a charge and bringing it from infinity and putting it at this location? No. But if I did take a charge and put it at this location in the presence of that guy, its potential energy would be exactly equal to the amount of work I would have to do to bring it from infinity to that location. Does that make sense? Okay, so while I'm bringing it in from infinity, it's going to feel two forces. I'm going to have an applied force, right? But there will also be a what? A repelling force, an electric force. And this is why I got to be super careful, because as I get closer, that force gets bigger, the electric force gets bigger. So I'm going to have to increase my force by the same amount to keep it moving at a constant speed, right? But just imagine that we could do that. And so as I'm moving this object from infinity to position R, this would be position X, but in general it's just R. I would be undergoing small displacements, incremental displacements you could call them, and I will call those incremental displacements dr. Because as I go from here to here, this is final position, this is initial position. That distance is the final position minus the initial position. That distance there. So that's why it's that length and it's pointing this way. That's dr. And then I just use the equation for work, the calculus equation for work. Remember, we had a definition for work, a real big kid definition. It's defined as the integral of f dot dr. From where to where? Well, the situation that you're dealing with will dictate that. What force? Doesn't matter. Any force. Really conservative forces. Not really conservative forces, but yeah, I'm sorry. Why did I say that? Can you edit that out of my video? No. Craig, thanks. Craig, right? No, Craig, sorry. Yeah, so it's the integral of f dot dr. If there's only one force acting, then it's just that force dotted with dr. Yeah. So if I want to do that I call this my applied force. So let's calculate the work done by the applied force. That's going to equal the integral from, and remember, we're going way out to infinity, and we're grabbing little q, and we're bringing it in from infinity to position R. And it's just the dot product of my force dotted with dr. Now think hard and tell me Because I got to have a function for the applied force in terms of r, right? In order to do that integral. What's the function? What's the function for that applied force? It's not constant, so what's the function?
It's equal to FE, which is...
Oh, well, we've got to be careful, but yes, you're onto something. You bypass, but we don't have a function for that. But we do know that if I did it very carefully, then yes, the electric force is just in the opposite direction, right? But it is the negative. So what I can do, though, I can say it's the negative of the integral of the electric force dotted with dr from infinity to r. Those are going to be equal, right? If I'm careful and bringing it in at a constant speed, those are going to be equal. What if I want to be fancy here? So now this is the work done by the applied force. Now we're talking. We could say the work done by the electric force, but I'm still saying the work that I have to do. Right? That's the left side here. The right side is where we made that. What if I don't want that negative there? There. Yeah, I could just go from r to infinity of the electric force dot dr. Right? Does that make sense? And if I do that work, and I evaluate that work with this integral, I will have calculated how much electric potential energy I have stored. And really, I'm sorry, it's really the change in electric potential energy. But don't focus on that. I'm sorry. It's going to be the potential energy stored. I'm jumping the gun here. I'm sorry. But does that kind of make sense? All right. We can do this problem because we have an equation for the electric force. The electric force, we are talking about charge little q being moved into the presence of charge big Q. So I think in the notes and in the, yeah, it's just K. We'll just use K so we can, it's a little easier to evaluate the integral. K, big Q, little q, over the distance between them squared. And so again, we're going to be integrating with respect to r, so we have to have the electric force expressed as a function of r. Well, it's a good thing we have the electric force expressed as a function of r. All right. So I'm going to plug those in, calculate the work done by the applied force is going to be, now what are constants here? Oh, sorry. I'm jumping ahead again. I need to plug in what F dot dr is going to be. And this you got to be careful. It's going to be the electric force times dr times the cosine of the angle between them, right? Is it positive or negative?
Negative.
Is this the right dr for that integral? I kind of messed up. If we're going from infinity to r, we are going this way. But if we're going from r to infinity, oh, this ain't the right dr for that one. We're going that way. How do I know that? Well, because I started r and I ended at infinity, right? Does that make sense? So imagine the reverse. Now the electric force is doing work and pushing it that way, right? It's the opposite, but the energies involved are the same. But I'm just doing what the integral is telling me to do. I'm going from r to infinity. So therefore, the dr that I use when evaluating the electric force will actually point that way. Not because we're actually bringing the charge over there, but because of the equivalence of the statements and because the math is telling me that what's really going on, which isn't what's really going on, because I'm really not taking a charge from infinity and bringing it here. But mathematically I am. And then I realize that mathematically that's the same result as doing an integral of the electric force dotted with dr going the other way. So all that to say that the cosine of the angle here is a positive one. And so yeah, the integral just becomes, or the work just becomes the integral from r to infinity of Fe dr, which shouldn't be a very difficult integral for us to do. Good times, right? So that's going to be KQQ over R squared. What of those are constants? KQQ. K big Q, little q. And then I'm going to integrate 1 over R squared, or R to the negative second, dr. So the work that I got to do to bring that charge in is equal to, from R to infinity, sorry. Well, you can't leave the limits off, right? Get marked off, maybe. I don't know. Did they mark you off for that? On the AP exam? As they should. So the work then is going to be KQQ times what? What's the integral of R to the negative 2 dr? Negative 1 over R. Evaluated from R to infinity. So the work done by the applied force is equal to KQQ times negative 1 over infinity minus negative 1 over R. What's negative 1 over infinity approximately? Because infinity is not really a number, but 0. So the force, the work done by the force will be KQQ over R. It's just like the electric force with 1 less R in the denominator. And that is the amount of potential energy that's now stored there. Okay? That is now, I'll just say the potential energy at that location. It's KQQ over R. This isn't generalized. We will generalize it more, but this is for a fixed charge and bringing another charge into the presence of that charge. Okay. Note that this isn't very general either. The work that I had to do in being very careful in moving a charge from infinity to that location, that's not very good either. That's not general. But I just know that this is the same as the work that the electric force would do in taking the charge from that position that way. So I'm answering the same question, right? And so I can just define the potential energy as the work done by the electric force in going the other way. So just kind of get that in your brain. But if you're talking about moving a point charge into the presence of another spherical or point charge type object, then it's just going to be KQQ over R. And you see that a lot on the AP exam. You have two fixed charges moving together, put together. How much potential energy? KQQ over R. That's it. All right. What else do I got? And notice by looking at it, this is the main idea. I don't know why I left it out. We don't want to use the applied force because that's not necessarily a conservative force, right? I don't know what type of force. I don't know what force I'm using to make this happen. I'm not pushing it. That'd be weird. But I know the electric force is conservative. The electric force, like the gravitational force, they're conservative forces. Therefore, the path that I take from going to infinity to this location doesn't matter. As far as the electric force goes, right? If that charge gets shot in here and it bypasses this point and then it goes back this way and then somehow comes back and then ends up there, the work done by the electric force in that entire time will be the same as the work done by the electric force when the charge just comes in straight and stops there. Why? Because the electric force is conservative. So the path that you take to get from one location to another doesn't matter. All that matters as far as the work done by the conservative force is the initial and final positions. Okay? This is where understanding what conservative forces are, or their implications at least, becomes pretty important. Because the electric force is conservative, and and it's not just from infinity. If I take this charge and move it here closer, I'm putting more potential energy in. So I'm going to have to do positive work this way. My muscles are still going to have to do work when I pull it back, so I'm going to get tired doing this. But from the electric force's perspective, I'm doing negative work. I'm doing positive work. I'm doing negative work. I'm doing positive work. Net work is 0 if you get back to the same spot, as far as the electric force is concerned. Does that make sense? Okay. That's why if I go from here to here and then back to here, well, the change in energy is 0, right? Even though the electric force did work the whole time, it just did Negative work when it moved this way, and positive work when it moved that way. Good times, right? I'm trying to get the concepts across before the math really gets in there. So, yeah. So notice we're talking about electric potential energy. Look that up. All right. So we know this guy makes a field, right? He makes a field in all directions surrounding it, pointing radially away if it's a positive charge. If there is an object within that field, it feels an electric force, right? The force needs a charge in that location in space in order to actually do something. But then we learn the concept of fields. Well, fields describe properties of the space surrounding the charge, whether there's a charge there or not, right? That's the beauty of fields, is that they allow us to describe stuff that exists in space even though nothing's happening, even though no work is being done. And we're going to do a similar thing with potential energy. Because potential energy, especially when we start getting to circuits and stuff, potential energy isn't a convenient way of going about doing things. There's something very closely related to potential energy that is far more convenient. And so now let's talk about relating, let me write it out. Electrical potential energy versus electrical, what am I going to say? Does anyone know? Potential. So this is a thing, and this is a thing, and they are not the same thing. But what electric potential does what electric fields do for electric forces, which again allow us to determine the electric force that would act on an object were it to be at that location in space. Electric potential does the same thing for electric potential energies. The electric potential energy of this charge requires that this charge be at that location. The electric potential at that location tells us how much potential energy per unit charge we would get were we to put a charge at that location. Okay. Sound complicated? Yeah, it's pretty complicated. So let's go back to electric fields. Electric fields are electric forces divided by charge. Look at the units. Understand the units at a gut level. Newtons per coulomb. Newtons per coulomb. If I have an electric field of 10, have we gone over the units of electric field? What's the units of electric field? We'll just say newtons per coulomb. If my field is 10 newtons per coulomb, and I have 2 coulombs of charge, what's the force going to be? 20 newtons. Notice that my electric force, sorry, I should have started with this, is Q times the electric field. Electric field exists without Q. If I put Q there, Q feels an electric force. The electric field is force divided by Q. Its units are newtons per coulomb. For every 1 coulomb of charge, you get 10 newtons of force if that field had that strength. Does that make sense? Because we're going to do the same kind of thing when we go to potential energy. The electric field is newtons per coulomb, meaning the more coulombs, the more force with the same field. Right? Okay. Potential energy, we just said in this particular configuration, is K, big Q, little q over R. Real easy to remember because it's the same as potential, or the same as electric force, but without an R. 1 less R. Also 1 over 4 pi epsilon naught times Q over R. I really should secure this. So this is potential energy. To define electric potential, we'll say this. Electric potential energy, I should say this, sorry, is the work required to bring little q to r. All right, we said that in words. And that's going to be the electric potential energy that is now stored there. Again, we want to look at the work done by the electric force, because that's the conservative force, so the path is independent. Electric potential energy is the work per unit of charge, key phrase, to put Q, to bring Q to R, sorry, to bring Q to R. It's subtle but not so subtle difference. Very important. Because this allows us to describe, again, properties of space without having to bring in another charge. If you want to know what the force on a charge in a place would be, you got to bring it in and measure the force. But if you know the field, then you know beforehand, well, if I bring this many coulombs of charge, then I'll get this force. Right? That's what the relationship, the electric field relationship tells us. Electric potential is kind of the same thing. An electric potential is a scalar field because electric potential is not a direction, doesn't have a direction, but it's still kind of like a field, so you just have a number at every point in space. And that number tells you the amount of potential energy that a charge would have if you were to put a charge there. How much potential energy? Determined by the amount of charge. More charge, more potential energy. I lift a heavier bowling ball, I store more potential energy, more gravitational potential energy. Same thing here, same thing. Cool beans? All right. So this is the biggie, and you'll really see why when we get to circuits. We deal with potential. We don't deal with potential energy. Okay, potential energy is not nearly as useful. Potential is much more useful. So let's talk about that a little more. The symbol for electric potential is what? Yeah. Capital V. The unit is, well, if it's work per unit charge, what's the unit? So we're understanding the units. Electric field, the units are newtons per coulomb. What is it? Work per unit of charge. Per means divide. What do we measure work in? Are we awake? Are we alive? Joules. What do we measure charge in? Coulombs. Are we alive? So what do we measure potential in? Joules per coulomb. Which is the volt. The definition of one definition of volt. We can define volts with other units as well that we'll talk about later in the year. That's the volt. And it is also a capital V, which is kind of annoying, but whatever. Deal with it. So if I wanted to say the voltage of 10 volts, I would say a voltage of 10 volts. Yeah. Sucks. Whatever. You don't really write stuff like that anyway, too much. Okay. It is a scalar, that's important. That makes our life somewhat easier. Again, it is a field, though. It fills space. It just doesn't have arrows attached to each location in space like a vector field, like the electric field does, or a gravitational field would. As we showed, I'm sorry, not as we showed, but as we will show now. The equation is essentially work per unit of charge. And so the voltage, write another color. Let me actually come up here. I'm going to erase this part. Remember this. You have that written. You have it written down. What am I talking about? So my equation, the voltage, at a certain point, and I could say the voltage or the electric potential. I'll probably say electric potential more just so we get that in our brains. The electric potential, meaning the electric potential energy per unit charge, meaning the work per unit charge required to bring that charge from infinity to that location, will just be equal to, well, the potential energy at the location divided by the amount of charge you want to put there. Work per unit charge, right? Well, we got an equation for potential energy. We just wrote it down, so I'm going to write it like this. 1 over Q times my potential energy, which is K, big Q, little q, over R. And what happens? Numerator Q, denominator 2, Q. You guys know what happens when you have something in the numerator and in the denominator? They cancel. They make a ratio of 1, therefore you can cross them out. I know, and I'm kind of giving you a preview of what's to come in university level courses. So my electric potential is going to be KQ over R. That's it.
Wait a minute.
Hmm?
I feel like I've seen that somewhere before.
It's close. It's related.
But without the square.
Yeah. Kind of like the electric field. I wonder if the electric field and the electric potential are going to be related somehow. Probably not. We'll see though. All right. Very often it's useful. It's useful for the same reason that, you know, the definition of the gravitational field is gravitational force per unit mass. This is the same way. We're doing the same thing but using mass instead of. So we never thought about it like this until this year. Last year we didn't. But yeah, this is gravitational field. It's equal to the force per unit mass, newtons per kilogram. Well, that's dimensionally equivalent to meters per second squared, so it's the same thing. But we use it more often because we want to know how much gravitational force we'll actually get when we place a mass m in a gravitational field. For the same reason, we very often take this guy, and if we're asked how much electric potential energy a system has, we just have to multiply the charge involved by the electric potential at that location in space. Does that make sense? Probably not, but you know. And if we have a simple configuration like this where we have a fixed charge, it's always this. The equation for the potential is always this. No matter where in space. Doesn't matter where. 3 dimensions all around the sphere in 3 dimensions. As far as you can go, the potential at any location in space will be K times the charge divided by the distance from the charge. The center of the charge. Yeah? This is some tough stuff to wrap your brains around. But you want to get them wrapped around it as soon as possible. So if you got questions, need clarification, ask Brian, because I don't know this stuff. Yep.
Why is it R not squared? Like, why is it not inversely proportional? Why is like R not squared? So why isn't
Because of the integral that we did.
Well, I mean, like, why isn't the amount of potential inversely proportional, like
To the square?
like the field strength?
Because it doesn't behave like the same way. It doesn't behave the same way. That's a good point. No, it's not inversely proportional to the square. It's inversely proportional to the distance without being squared. Interesting. That's a good question. One of you guys is thinking about this stuff. Just kidding. There's only one of you in here. All right. That's a good question, though. I probably didn't answer it that well, but I don't know. Maybe it'll become more apparent as we go on. Yeah, when we do the integral, this will be dimensionally equivalent to, if I do the units of K and Q and R, I'll get units of joules per coulomb. But you got to put in the units for epsilon naught in the denominator, you know, when you do that. And it's just the whole big thing. Feel free. Everything on your formula sheet. Everything that you need is on your formula sheet. So yeah, so that's important. We're going to be using this a lot. Using that quite a bit. All right. If this is positive, the electric potential will be positive. If this is negative, the electric potential will be negative. Yes, you can have negative electric potentials. So, yeah, there's that. For a system of multiple charges, and you might see questions like this. Actually, we'll come back to that later. I want to do something a little more fun first. Let's say that this is a Van de Graaff generator. So it's like that guy over there. And we want to know what the electric potential on the surface is, meaning what is the voltage on the surface of your typical Van de Graaff generator. Well, a typical Van de Graaff generator, let's try it here. Typical Van de Graaff generator can store approximately 2 microcoulombs of charge. So that's Q. The radius, typically about 20 centimeters. I did 15 here. 0.15 meters. Our new Van de Graaffs will have larger radii. They're going to be fun. Now we know that when that gets charged, what does the charge do? It's metal.
It accumulates on the surface.
Accumulates on the surface. So all the charge goes to the surface, and then it acts like a point charge outside of it, right? So when a question says what is the potential, electric potential on the surface, it's like the voltage on the surface, the voltage right on the surface. But even if it's right on the surface, you still treat it as a point charge. Okay? You only stop doing that once you go below the layer of charge. All right. So let's look at it this way. Let's look at our equation for work, which we've been using all day. That's going to be the integral from r to infinity of the electric force dotted with dr. Right, we want to use the electric force because that's the general version. That's the general force that I can describe at every location in space. If I'm actually talking about the work I do, it's much more complicated. Much easier to do it this way. And then I'm going to, because I can do anything I want, as long as I do it to both sides, I'm going to divide both sides by little q. So I divide this side by little q, and I divide that side by little q. And little q it doesn't matter what it is, what its actual charge is, but I'm going to make sure it's constant. So I'm going to stick it inside the integral. Okay. But what's work per unit charge? What's the name for that again? What's the name? The voltage, or the electric potential. Oh, it's going to be the integral of Fe over Q dotted with dr. I'm not going to go into the properties of the dot product, but when you divide a dot product by a scalar, you can just divide one guy by it or divide the other guy by it. Doesn't matter. You can still do the dot product afterwards, and you get the same thing. So it doesn't matter. So I'm going to put it there. Why am I going to put it there?
So you can turn it into E.
So it's good. So I can write that as the electric field, right? So the electric potential is going to be the integral from r to infinity of the electric field dotted with dr. And in this case, what you'll get, it's pretty trivial. Electric field KQQ over electric field KQ over R squared. So we should have something that looks like KQ over R at the end. You can do that integral if you want. Just electric field is KQ over R squared. Almost the same integral as the one we already did today. But that's going to be the result. It's KQ over R. Didn't we already do that? We already did that. Yeah, that's the electric potential on the surface of a charged conductor. Spherically symmetric charged conductor. you're going to have a lot of questions about that. You're going to have a lot of questions dealing with charged metals, charged conductors, and dealing with the electric potential on their surfaces. And then maybe having another smaller conductor, also a conductor, and then connecting them with the wire. How does the charge distribute? Amongst two equal conductors, you might be able to guess, but different sizes? So and to answer those types of questions, it's all about the voltages on the surface. But again, voltage due to a point charge is just KQ over R. Okay? On the formula sheet, let's talk about the formula sheet. I know I have one up here, but oh my gosh, that is a mess. And Jacob Casillas has left me one formula sheet. So how is all of this written on the formula sheet? I'm not going to talk about potential difference yet. Usually when we talk about voltage, we're talking about something called potential difference. But these are on the formula sheet. The potential energy, UE, is equal to Q times the voltage. Scalars, nice, scalars. That is on the formula sheet, followed by 1 over 4 pi epsilon naught. Instead of Q, they have it written like that. Times Q1, Q2 over R. Remember, you got to have both Q's there because to actually have potential energy, you have to assemble a configuration of two charges. Otherwise, the charge just sits there and it doesn't do anything. Can't do any work. No energy. What else? The electric potential, which we've been talking about, which we've been talking about. Oh yeah, that's AQ over R. It's written like this: 1 over 4 pi epsilon naught times the sum of all the QI over RIs. That just means if you have a collection of point charges. And I'm not going to do that one today. We're going to do that one tomorrow with the little bit of time that we have. But what this is really referring to is, let's say I bring this charge Q1 here. Okay, that doesn't require any work. From the electric force, the electric field standpoint. Because there's going to be no electric force because it's only one charge. But if I bring in another one and say put it here, all right, I'm going to have to do work to bring that guy there. And then I'm going to have to do work to bring Q3 here. And I'm going to have to and the more I do this, the more work I'm going to have to do, right? Right? And so you might get a question that says, what's the electric potential at a point right here? This is why it's nice that the electric potential is a scalar. Because we don't have to worry about vectors or decomposition or anything. All we have to do, well, let's talk about it now. There will be an actual example on the notes that I'll have for you tomorrow. If I want to know the electric potential at point P, well, I have 4 point charges, each with their own potentials, KQ over R, at P. And so that's what I do. I just say, okay, well, this right here is going to be R3. This guy right here is going to be R4. This guy right here is going to be R2. This guy right here is going to be R1. And the electric potential there, you could say like the net, is just going to be the electric potential at 1 plus the electric potential at 2 plus the electric potential from charge 3 plus the electric field from charge 4. Electric potential, why am I saying field? And then each one of these is just K times the respective Q divided by their respective difference. Okay? It sounds complicated when you say it. Well, I bring one charge in and then do a little more work to bring this guy there and then a little more work to bring this guy in there. And so it would be complicated to actually make it happen, but from the standpoint of the electric force and the corresponding electric field, the potentials involved, it's just the sum. It's just the sum. And they're all just KQ over R. If Q is negative, then it is negative, right? If one of these charges is negative, then it requires less work to bring more positive charge in. Because the negative charge is going to kind of give you a little boost. It's going to help you. So those potentials would be subtracted, all right? Again, we'll do a more concrete example where we have charges actually placed on an XY grid where we can calculate something like that explicitly. All right. But yeah, take home point. The definition of potential with the integral does not look like this on the formula sheet. It is a delta V. And there's some other shenanigans that go on here that we'll talk about maybe tomorrow, maybe next week. It depends. You might watch it in a video, actually, because we got some makeup to do. Anyway, back to this guy. That was a small aside. I apologize. In this case, we're still going to use this guy, but there's only one charge and one distance I need to worry about, right? So for us here, I'm going to use V, and I'm just going to use K because that's what I'm going to do, times this charge, Q, over the distance. Well, I want to know at the surface because that's where I'm interested in the electric potential or the voltage on the surface. Well, that's a distance R. All right, well, that's going to be the electric potential on the surface of my Van de Graaff generator. So let me plug in those numbers. 9 times 10 to the 9th times 2 microcoulombs, 2 times 10 to the negative 6th, divided by 0.15. And you get a voltage of approximately 120,000 volts. And I think it's a little higher than that. I think there's other stuff. The ones that we're getting hopefully soon. I don't know how soon. 400,000. So yeah, maybe three times stronger than these ones. So most people see that and they're like, wait a minute. Why is that not dangerous? Unless you're weak sauce and you don't want to get shocked because it hurts. But yeah, what? They're not dangerous. Yeah, they're at 120,000 volts. You know what you know what that voltage is, right? 120. I think that's why they picked those numbers. Yeah, the voltage on this guy is 1,000 times greater than the voltage that you tap into when you plug something into the wall. Are you afraid of the voltage in the wall? You should be. You shouldn't mess with it. If something is amiss and you got wires hanging out of your wall, you better not touch it unless you really know what you're doing. At least get a little voltage thing, like $10 at Home Depot. Save your life. But yeah. So why is that? Well, the wall's got a limitless source of charge from the power company, right? Limitless. The sphere here has only a certain capacity to store charge. Hence capacitor, right? We've used that word before. This is a capacitor. If you can store charge, you're a capacitor. It's just not a good capacitor, as we'll see when we start studying capacitance. This guy stores charge. It can only store about 2 microcoulombs based on its configuration. It's not designed to store a lot of charge. If it was, then it would become dangerous. So it's designed to do experiments with static electricity and to do fun stuff like make kids' hair stand up so they laugh. But yeah, it can't store that much charge. 2 microcoulombs ain't going to kill you. It's not. 2 coulombs definitely going to kill you. But 2 microcoulombs not going to kill you. You'll be fine. Make sense? Kind of? Sort of? All right.
So what if it had like a lot of charge, but like 1 volt of electric potential?
Yeah, you're going to be all right. 1 volt isn't going to be able to push a lot of charge. Yeah. You're talking about circuit stuff we'll definitely get to, but if you're talking circuits, the voltage is like the pump. And the current is like the stuff that the pump's actually pushing. So you can have a really strong pump, like the outlet there, and 0 current because it's not actually pumping anything. But if you give it a pathway to pump something, then it's going to pump something. And that pathway could be you, right, if you're not careful. Same thing. So, and this thing, if you store charge on it, has the ability to pump charge off of it. And it has a great ability to. But there's not a lot of charge. So when it does pump all the charge off of it, it's just a little spark, right? It's fully discharged, and all it was just a little tiny spark.
So does all of that charge come off at once? So
that's a good. It's not that like say you say it's negatively charged, and you build up an excess of 10 electrons, right? And they're evenly distributed, and then you get zapped. It's not that those exact 10 electrons jump onto me. It's that the electrons reconfigure themselves so that I get the zap and so that I discharge the excess charge, the total charge, But the electrons are just moving around until they feel a net electric force of 0, where the electric field inside will be 0, and then they're just going to be chilling. So they just reconfigure using you as a conduit to eliminate the excess energy. If you want to look at it as energy, it might be a little easier. That's a good question, though, because a lot of people think, oh, it picks up charge and you touch it and all that charge comes off on it. No, it's just the reconfiguring of the electrons themselves and then using you to just as a way to discharge the excess charge that is remaining as the electrons are moving around.
So is that the same like in like a wire or something? Something that like carries. So like in the wall, for example, if you were to touch that, like what's the difference between touching that and touching the transgraph generator?
The wall has a limitless source of charge.
So like, but
Like even if you're getting shocked, it's not going to stop going through you because it's continuously.
But like you said that like nothing, no like physical things are actually moving between you.
No, electrons are actually moving. It's not the exact electron because when say you have an excess of electrons, well, you have just as many back here as you do here. But when you get shocked here, the electrons here did not move over to here. They redistributed because as my hand gets closer, I get polarized, right? So I start influencing the electric field. So even before I get shocked, the electrons are rearranging themselves due to that influence of this new electric field. By the time I get shocked, well, then they're going to like immediately rush to be completely neutral because now I've discharged the excess charge. And so the electrons that will go through me, though, will come from where I'm next to. Okay. And then the holes get kind of filled in as everything just kind of comes forward like that. Yeah. That's a good question. You're making me think, man. Gosh. It's not part of my job description, you know. What was that, sir? Oh, yeah. I feel like I'm going a lot slower than I should. But, are you guys doing that? I think I want to do just a couple more things real quick. So that's about 120,000 volts. So let's talk about, this will be the last thing. I want to take this Van de Graaff generator. And we did this before with electric fields, right? I want to plot not the electric field per distance or not the electric field versus distance, but versus position, I should say, but the electric potential per position versus position. I cannot talk. What is wrong with me? Oh my gosh. So, I'm going to graph it directly underneath. So obviously this is positive R, this is negative R, and I want to plot electric potential versus position in the x direction. So I'll be going this way. Hopefully, we know what it'll be on outside of R and negative R. What's it going to look like? Think of this as R. So here it would be KQ over X. This graph of Y equals 1 over X. Thank you, Craig. Aren't they inversely proportional? Is this too much for today? Do we need to stop? Right, we have this new equation, Brent. We have our new equation. The electric potential due to this charge outside from the surface out to infinity is equal to K times the charge stored on it divided by R, where R is the distance from the object's center. So the voltage is inversely proportional to the radial distance outside of the charge. So what does the graph look like, Craig? There you go. And actually, maybe not all the way up to infinity there. Sorry. It'd be like, because it's not infinity there. right? There's no asymptote there. Because at R, we have a potential. The interesting thing happens when we go where? Inside R. Inside R, what's the electric field?
0.
Electric field is 0. So the electric field 0. What do you think the potential inside is?
0.
Is it? Infinity?
You don't have any charge. Or net charge.
There isn't any charge on it.
Inside.
How about this? Whenever asked what the potential is, or if there is potential, or if it's 0, ask if there's potential energy. If you were to put a charge there. If I was to put a charge inside here, would it have potential energy?
Yes.
It would. Because if I were to just push it a little bit until it goes to the other side, what happens? Right? And it converts that potential energy to kinetic energy. And I didn't have to do any work to move it because the electric field is 0. So it didn't require any work. I just flick it and it goes, and it takes off, right? That makes sense? It's like this. The gravitational force is doing no work in moving my mouse around, right? Does my mouse have potential energy? Yeah, all I have to do is push it off. Yeah. You didn't see it on the video. Hopefully you heard what I was talking about, though. Yeah. So it's like, yeah, so there's actual potential energy there. What can I say about the potential energy of the mouse as I move this around on the tabletop? It's constant. So what do you think the electric potential energy of any charge in here is? It's going to be constant. If the electric potential is constant, potential energy is constant, if I were to have a charge there, what do you think you could say about the electric potential inside there? It's constant. So it probably makes a little table looking guy like this. And I think we can probably stop there. We can talk about the math that proves this, but we'll do that tomorrow because I think I'm done thinking for today. What? Well, the electric field would look very much the same, but it would be 0 here. If it was the electric field for a charged insulator, then it would be linear, and then it would be 1 over x squared. All right. That's it. I hope you enjoyed the video. Brant and Alex and Jacob and Julie and all my other favorite students. Smash the like button, but don't subscribe or ring the bell.